The conservation of energy. This is sometimes called the first law of thermodynamics. Basically what it says is that energy cannot be created or destroyed, but it can be transferred from one form to another. So what's an example of that? Well, I can take gasoline, which is chemical energy, I can put it into a car and I can convert that into chemical energy, the motion of the car. Or I can take potential energy in a compressed spring and I can use that to fire an object and convert that into kinetic energy. So in these systems, the overall energy remains the same, it's just moved from one form to another form. Okay? So oftentimes when we solve physics problems, we'll say, for example, say the potential energy, the initial potential energy, which I'll call PEI, let's say of an object at a certain distance above the ground, is going to equal the kinetic energy final of that object right before it hits the ground. Okay? So this is a good example of the conservation of energy, or the first law of thermodynamics. Okay? So what's a problem where we might look at something like that? Well, let's say we've got an object, let's say a TV. This might be a fun thing to do at home, but don't try this at home. 5 kilogram TV is dropped from a 2-meter stand, and I want to know what the velocity is when it hits the ground. Okay? Well, so I'm giving you potential energy here where it's positional energy, right? It's a certain distance above the ground, and it's going to accelerate until it hits the ground. And when it does, it will have a certain amount of kinetic energy. So let's say our initial potential energy is going to equal our final kinetic energy. Okay? So first off, what's our initial potential energy? So the formula for potential energy is PE equals mass times force of gravity. In this case, we'll say 10 meters per second squared times the height of the object. Okay, so let's look at that. We've got the mass of the object is 5 kilograms, and the height is 10 meters per second squared, and the height of the object is 2 meters. Okay, so I've got a mass, an acceleration, and a distance, and that's going to give me a total amount of energy. If I multiply these out, I get 5 times 10 times 2 equals 100, and the unit for energy is joules. 100 joules of energy in that TV up at that distance. Okay? So that amount of potential energy equals the amount of kinetic energy right before it hits the floor. Okay? 2 meters below it. So let's go ahead and say I've got my initial potential energy, and it must equal my final kinetic energy. There we go. So my initial potential energy was 100 joules. Okay. So what's my final velocity? Well, remember the formula for kinetic energy is 1/2 times the meter. I'm sorry, 1/2 times the mass, not meter, mass times the velocity squared. Okay. So if I carry that down and plug in my numbers, 100 joules equals 1/2 times 5 kilograms times v squared, because in this case we want to know what the velocity is, the final velocity. Okay, so now to get rid of this in front of my velocity, right, I've got 1/2 times my kinetic energy. That must equal 2 times my initial potential energy, right? And if I'm multiplying it times 5, that must be the same as dividing this by 5 kilograms, okay, which equals my velocity squared. Okay, so if I multiply that, I get 200, and I divide that by 5, I get 40. And in this case, when I reduce the units, since there's a unit of mass in here, I'm just ending up with a distance times a distance squared. So 2 meters squared over second squared, and that equals v squared. Okay? So solving for v is going to equal 6.32 meters per second. That's the final velocity of my TV as it crashes, right before it crashes into the floor. Okay, so this is a good problem with potential energy being converted into kinetic energy, and it's showing this conservation of energy. The total energy in the system does not change, it's just being converted from one form into another. And that's how you use kinetic energy and potential energy to solve a problem related to conservation of energy.